This is the 6th lecture in the FOA series on fiber optics. This lecture covers fiber optic splices. Splices are used to join two fibers permanently. Typically, they're used for concatenation, that's a big word for joining, of cables for long cable runs, or to splice on pigtails for termination. They can also be used for the restoration of cut cables. Splicing works with either single fibers or multi-fiber ribbons, which can be done all at once. The requirements for fiber optic splices are the same for any other fiber optic joint. Splices must have low loss, low reflectance, high mechanical strength, long-term reliability, and of course be easy to use in the field. There are two types of fiber optic splices, fusion and mechanical. Fusion splices use a large automatic machine to weld two fibers together, typically in an electric arc. Mechanical splices use a mechanical fixturing to align two fibers with index matching gel in between them and clamps on either side to hold the fibers in place. Fusion splicers are expensive machines, fully automated, that do most of the work for you. The operator uses a high-quality cleaver to prepare the ends of the fibers and inserts them in the jaws of the splicer. The machine automatically aligns the end, makes the splice with an electric arc, and gives an estimate of the loss. The finished splice is covered by a protection sleeve and placed in a splice tray. While fusion splicers are expensive, each splice is cheap. So if you're doing lots of splices, fusion is more cost-effective. Here's a typical single fiber fusion splicer with the tools and cleaver you need to use it. The splicer includes a display that will show you the fibers being aligned and fused and give you information about the progress of the process. Here's a ribbon fusion splicer. These machines are bigger, more expensive, and more complex, but they fuse 12 fibers at once. They require special fixturing, but since so many ribbon fibers are used in today's marketplace, they're very popular and are very, very good at improving the installer's productivity. Fusion splicers typically use two different methods of fiber alignment: local injection and detection, where it puts a stress on a fiber and couples light into the fiber and measures the light coming out on the far side of the splice to optimize the splice. Profile alignment systems look at the fiber from two directions and align according to the core of the fiber, which you can see through the fiber itself. The fusion splice process is straightforward. You strip, clean, and cleave the fiber and place the fiber in the jaws of the splicer properly. Repeat with a second fiber, close the cover, start the automated program. The splicer will complete the splice and estimate the loss. When you're through, you remove the fiber and place the splice protector over the splice. Here's the screen of a single fiber splicer during a splice. First, it pre-fuses the fibers to warm them up and clean the dust off. It aligns them and fuses them. During the process, the screen will show fiber alignment and give you messages to describe what process is being done at the time. When finished running the program, the splicer will show the splice loss estimate at the top of the screen and indicate the splicing process has been completed. Mechanical splices use some mechanical alignment fixture, such as a glass capillary, a V-groove, or some kind of metal clamp, and some means of securing the fibers in the splice. Mechanical splices are more common with multi-mode fiber, but are sometimes used for single-mode restoration until fusion splicing can be done. Mechanical splices themselves are more expensive per splice than fusion splicing because of the mechanical fixtures, but the equipment necessary is relatively inexpensive. So if you're only making a few splices, mechanical splicing may be the less expensive choice. Mechanical splicing is very similar to fusion splicing. You strip, clean, and cleave the fiber, and then simply insert it in one end of the splice fixture. Repeat for the second fiber. Both the fibers have to be pushed against each other to make sure that the index matching gel in the middle is fully distributed. If needed, the loss of the splice can be optimized with a visual fault locator. Many types of mechanical splices can be optimized using a visual fault locator, an instrument that injects a bright red visible laser light into the fiber. By moving one of the fibers in and out and mating it differently to the other, you can minimize the light lost at the splice, which tells you you've gotten the best splice you can get. In order to get good fiber optic splices, it is important to cleave the fiber properly. Cleaving is the process by which an optical fiber is cut or precisely broken for termination or splicing. Just like cutting glass plate, the fiber is cut by scoring or scratching the surface and applying stress so the glass breaks in a smooth manner along the stress lines created by the scratch. Properly done, the fiber will cleave with a clean surface perpendicular to the length of the fiber, with no protruding glass on either end and no surface roughness. The quality of the cleave is usually a function of the cleaving tool. A good cleave yields a perpendicular end face to the axis of the fiber, has no lips or chips where the fiber edge is exposed, or hackle where the glass is broken away from the glass of the fiber. The fiber should have a good, clean end face free of cracks, chips, and scratches. The angle of the fiber should not be visible. If there is any appearance of flaws, the cleaving cycle should be repeated. There are a number of types of inexpensive handheld cleavers like this one shown here. They're often supplied with manufacturer's kits for mechanical splices. They require practice and skill to get good cleaves. This more sophisticated cleaver is like the types provided for fusion splicers. It requires little skill or practice and provides virtually 100% good cleaves as long as you carefully strip and clean the fibers before trying to cleave. While it is much more expensive than the handheld types, it quickly pays for itself in higher yields and productivity. Splices always require protection from the environment. Completed splices are inserted in a splice tray, which goes in a splice closure. Incoming cables are secured to the closure for mechanical strength and sealed. Loose tubes on the cable are secured to the splice tray, so the bare fibers are only exposed inside the tray. The closure is sealed to protect the fibers and splices from the outside environment. Closures can be buried underground, placed in vaults or manholes, supported on aerial cables, or even poles, depending on the cable installation. This is Lecture 6 in the FOA series of lectures on fiber optics. Look for more FOA lectures and videos on the FOA YouTube channel. We're the Fiber Optic Association, Incorporated, the worldwide professional society of fiber optics, promoting fiber optics through education, certification, and standards. You can find much more information on fiber, especially good technical information, on our website.